In this lecture, I'm going to talk about variation, the concept of variation, not the mathematics of variation. It's very important to understand the concepts of everything before you really try to delve into the math of it. And well, you don't have to be super great at the concepts of everything, but variation is one of those concepts that it's better to know what it means first before you delve into it. Because there's no math required on this, the prerequisite is none. We don't have any math prerequisites. We'll start with a conceptual definition of what's known as direct variation. It's a flawed definition that we'll find out why it's flawed when we start talking about the mathematics in the next video lecture. But in this video lecture, for right now, we're just going to assume that this is the definition. When one quantity increases as another quantity increases, we say that the first quantity varies directly with the second quantity. So as you basically, this means you have two variables. You increase one, it causes the other to increase as well. Now, like I said, it's somewhat flawed because it has to be a little bit more technical to actually be direct variation. But that's the basic conceptual ideas. You increase one value, the other one has to increase as well. So let's take a look at some conceptual examples here. First one we have is if you have an hourly wage, let's say $8 an hour or $9 an hour, $10 an hour, your paycheck varies directly with the number of hours you work. In other words, you work more hours, your paycheck is higher. Right? So as you increase one variable, the other variable increases. And notice the wording here. There's two types of wording you'll generally see with variation problems, at least with direct variation problems. One is varies directly, and the other one we'll see in a moment, but you'll see it down here. It's directly proportional. So I could have said your paycheck is directly proportional to the number of hours you work. So if you see either of those wordings or you hear somebody say that, they mean the same thing. They mean that as you increase one, the other increases. As you decrease one, the other decreases. They go in the same direction. Now the second example, the distance between a storm and you varies directly with the time interval between the lightning strikes and the thunder. You ever heard that, right? You see a lightning strike and you start counting, and then once the thunder goes off, you know that's how many miles away it is. It's not really true, it's a rule of thumb, but good enough. So in other words, the further you are away from the storm, the longer the time interval is between lightning strikes and thunders. The closer you are to the storm, well, the closer the time interval is between the lightning strike and the thunder. That's a real world variation problem. And the last one is more of a physics-y problem. Hooke's law states the force needed to keep a spring stretched at a certain distance beyond its natural length is directly proportional to that stretch. In other words, the amount of strength you need to maintain a stretch on a spring is directly proportional to the stretch that you're pulling on that string. I say string, I meant spring. So let's suppose that this is a spring and you have some mass attached to it and you want to pull this down. The black curve will be, let's say, just when nobody's touching that spring, and the gray curve will be actually what you stretched it to. The amount of force that you're pulling this with and holding it with is directly proportional to this distance that you've pulled it, that distance right there. That's what Hooke's law basically says. The more you want to pull it out, the more force you're going to have to use. That should make sense. Many things in the real world follow variation like this, direct variation, or as we'll see in a moment, something called inverse variation. But it's so important that you really understand these concepts, that as one item or quantity increases, then the other one increases. As one item decreases, the other one decreases. They vary together. The second definition, conceptual definition, is for inverse variation. And again, this is somewhat flawed. This is flawed because we're not really using the mathematics behind it. However, this will be good enough for the language and for the concepts. When one quantity decreases as another quantity increases. So in other words, we have opposite directions going on here. We say that the first quantity varies inversely with the second quantity. And actually, you could say the second quantity varies inversely with the first quantity. That's actually true. They both vary inversely with each other. So let's take a look at some examples. And like I said, remember, we're looking for examples where when you increase one quantity, its related quantity decreases. So for example, from physics, Boyle's law states that when a gas is compressed at a constant temperature, so you have some gas at constant temperature that gets compressed, the pressure of the gas is inversely proportional to the volume of the gas. So you can kind of think of it this way if you want to really understand the concept. We can illustrate this by using a simulation from Wolfram's demonstrations project, and that is available on Wolfram. Just Google Wolfram demonstrations project. The one that I'm going to use here is simulation of a simple gas pressure model. Now, you don't have to be a physicist to enjoy this. This is actually pretty neat. You can modify the number of atoms in the model if you want, but I'm just going to keep it at kind of a nice solid mix. And you can modify the temperature of the model. Now, just to let you know, if you know anything about physics, you heat up a gas and the atoms move faster and faster. So you can see they're moving fast. Okay. So that's that. I'm going to keep the temperature kind of low here. So you see the atoms are still kind of moving quickly. Now, what we had just said about Boyle's law is that when a gas is compressed at a constant temperature, so the gas we'll assume has a constant temperature, and when we compress it, the pressure of the gas is inversely proportional to the volume. In other words, as we increase the pressure of the gas, the volume should decrease. Or better yet, if we increase the volume, the pressure will decrease, or if we decrease the volume, the pressure will increase. They go in opposite directions. So let's take a look and see if that works in this modeling application. I always find it's more important to visualize here. So the container size is actually our volume. Now remember, Boyle's law says that if we increase the volume, the pressure should decrease. Here's our pressure. It's roughly around 11.5, 12. It just depends. It's all about these atoms bouncing up against the edge of our container. So let's increase the size of our container. And as we do that, you see the pressure has decreased. Pressure has decreased down to what, 4 or 5, somewhere around there. You kind of see why, because there's still the same number of atoms in there. They just, fewer of them are hitting the wall at any given moment. And I can even increase the volume more, and again, the pressure will actually decrease even more. We're down to what, 3? Well, no, 3, 3.5, 3 now. If we decrease the volume to a very small volume, all of a sudden the pressure skyrockets. It goes from about 3 to about 40. And I can make a really tiny container, and that pressure should definitely spike up. So that's a great visualization of Boyle's law. Example B here says that the temperature of a specific layer in the ocean varies inversely with the depth of that layer. In other words, as you decrease, or in other words, as you increase the temperature, the depth is decreased. So we're only a foot deep into the ocean. If you increase the temperature more, that means your depth is less. If you decrease the temperature, your depth is more. That should make sense, right? The deeper you are in the ocean, the lower the temperature. You have to sort of use a little bit of language manipulation here, by the way. When I say depth, I'm really talking like the deeper you are in the ocean, it means the more depth you have. So that means increased depth means decreased temperature. A little bit of a word play on there. By the way, you already see that I've highlighted 2 versions of how inverse variation problems are labeled. One way they'll say something is inversely proportional to another. The other type, they'll say these 2 objects vary inversely with each other. So there you have those two examples. Finally, example C here is just the number of hours it takes a cube of ice to melt is inversely proportional to the ambient temperature. If you increase the ambient temperature, it decreases the time it takes to melt the ice. If you decrease the ambient temperature to near freezing, let's say, it significantly increases the number of hours it takes to melt that cube of ice. Now, I hope that this has helped you find a better conceptual visualization of variation problems. After this, you should really attempt some variation to, well, maybe you should actually attempt to find your own variation problem. So participate in your own education. Take some time to determine what other real world quantities vary directly with each other, and try to find some that also vary inversely with each other. It's actually not that difficult, but it's good for you to spend some time thinking about this. Part of mathematics is creation and critical thinking and problem solving, and what you want to do is play with math a little bit before you do the mathematics. Just try to visualize so you can really think of some really interesting and apropos stuff that fits better to your life. If you are big on computer gaming, or if you're big on sewing or painting or music, you can find something in your own hobby that you can find maybe two things that vary directly with each other or very inversely with each other. Give it a try.